Unit 7 progress check. Free response question part B, number 1. There is one key word in this that's going to set us on fire mathematically. Liquid fertilizer is injected into a hydroponics growing system via a pumping system. The total amount of liquid fertilizer injected in the growing system by time t is modeled by the function f. Okay, there's some function f. Satisfies the logistic. Stop right there. Here's logistic. I just drew a graph. Offhandedly, just very quickly drew a graph a few minutes ago. And this is what it looks like. You can't sustain exponential growth forever. It has to level off. And so this will be your carrying capacity right here, whatever this population is. In the context of this problem, we're not dealing with population. We're dealing with the amount of fertilizer, measured in liters, that is pumped into this system. Just wanted to point that out. Here's the differential equation. If we don't know this next part, we're really going to have a hard time moving forward because a lot of what we need to know depends on understanding what that number 6 means for real. Number 6 is the carrying capacity. That's it. Our carrying capacity is 6 liters, which means as time goes on, we haven't even finished reading the problem, but I'm telling you things that should go through your head. As time goes on, we're eventually going to reach not a population, but a carrying capacity of fertilizer of 6. We're going to get super duper close to 6. Never quite reach it, but we're going to get really, really close to it. 5.999. T is measured in months. F is measured in liters. At time t equals 0, 3 liters of liquid fertilizer are injected into the growing system. Hydroponics tells you all about it. Wonderful. Let's look into it. Grow some stuff. All right. Part A has a couple parts. Part 1, Part 2. I've just wrote them here. Instead, you don't have to write the Roman numerals. And we will go ahead and begin. Actually, I'd already written the answer and had to white it out. So the limit as t approaches infinity for the function. Now, you might be looking at this and say, oh, well, then let's separate the variables. And you grab your paper and you're like, well, I'm going to move my dt up here. And I'm going to be like, okay, divide by all that. And then don't. You know it's logistic. As time moves on, you're going to reach your carrying capacity of 6. Really, like for real, 6. Okay? Well, how does the rate change? Let me rephrase that. As time approaches infinity, what value does the rate approach? As long as you know what the graph of this looks like, then you'll know the answer to that. What's the slope as we get further and further and further out? We're getting closer and closer to this horizontal line, and the function itself is approaching it, and so it's becoming flatter and flatter. So as we approach 0, the slope approaches, as we approach infinity, as time approaches infinity, the slope of the function approaches 0. That's it. There was no fancy math on that. It was all an understanding of logistic functions. Part B. Okay. Find the value of df dt at the time when f is increasing most rapidly. Okay. Now, there is a very complicated way of doing this. If I want f to be increasing, that's a derivative. Rapidly, that's the second derivative. We're talking about the rate of change of the rate of change. We could take the derivative of our derivative and set it equal to 0. By the time you do that, 15 minutes have passed, and you will not be able to finish this problem. So let's not. Okay. Instead, the function is increasing most rapidly. This is another logistic thing to know. Function is increasing most rapidly when you have reached half of your carrying capacity, which based on the graph I have is 3. Okay, based on this equation is 3 because it's half of 6. And then it says give a reason for your answer, or what, justify your answer. Give a reason for your answer, indicate units of measure. Okay, when I have reached half my carrying capacity, which would be 3, then the function is increasing most rapidly. Notice that my slope is pretty much 0 here. It's increasing, my slope is increasing, slope is increasing, slope is increasing. Now my slope starts decreasing. It's point of inflection. It's where my concavity changes. So let's just write it. Here it goes. F is increasing most rapidly when the amount of fertilizer, or you could say F, or you could say F of T, when the amount of fertilizer is half of its carrying capacity, which is 3 liters. Okay, we haven't answered the question yet. We've actually already given a reason for an answer that we haven't even stated. So it said give a reason for your answer and indicate units of measure, but I still need to find the value of the derivative at that time. So we are going to, well, find the value of the derivative. The value of the derivative when F equals 3, not when T equals 3. Actually, T equals 0 because they told us that. By the way, here's how we know that. 3 liters of liquid are injected and T equals 0. So the point of inflection is actually on the y-axis in this case. It would be 1/3 times 3 times 6 minus 3. I'm not making these numbers up. 3 goes here, 3 goes here. That gives me 1 times 3, so 3. 3. But indicate units of measure. All right, 3 what? Oh, liters. No, not liters. Not liters. This is a rate of change. Okay, this is a rate of change. The rate of change happens when the rate of change is maximum when I am at half the carrying capacity, which would be 3 liters, but the rate of change is measured in liters per time measurement, month. It's a long process. We're growing plants. Okay, part C. Find the second derivative in terms of F. All right, you can do that. Let's start by writing the first derivative again, just so I'm not having to slide back and forth here and here and here and you get dizzy. So the first derivative is 1/3 F, 6 minus F. Okay, we're going to write this in terms of F. So the second derivative, this is product rule. F prime. All right, the derivative of 1/3 F would be 1/3 df dt. That's F prime G plus F, little f, like dealing with the formula, okay? Maybe I shouldn't use F's and G's here for the formula. And then G prime, which would be -1, and then df dt. Implicit differentiation, I'm taking the derivative with respect to time, and every time I take the derivative of capital F, I'm going to need this capital, or d capital F dt. I'm going to need that. So this is it. Let's work on this, because this is sloppy. It is quite sloppy. Let's clean a few things up. We have 1/3, let's see, 1/3 df dt, and 6 minus f. What I'm doing here, in case you really care what I'm doing, minus 1/3 f df dt. What I did, and this is not the only way to do it, but what I'm doing is, whoops, I need df dt here. I'm just rearranging these terms and making them a little bit neater. And now, I'm not done. You might be like, yeah, found it. Right. No. They said in terms of f. So by the time I'm done, I better have nothing but like f's here. F's and numbers. So that's it. So 1/3, 6 minus f, and then df dt. Oh, df dt? Well, what's that? Oh, well, it's this right here. It's 1/3 f, 6 minus f. That right there is our original derivative. See? There it is. Plus 1/3 f. Whoops. I did it again. Minus 1/3. And then df dt. Now, when I worked this one out myself, actually what I did was I factored out a 1/3 df dt from both of those. It works out beautifully. I don't know why I didn't do it this time, but I didn't. But it's all going to work out in the end. This is a little bit sloppier than I have done in the past, so let's just keep going with it. Let's factor everything that factors. So both of these terms have a 1/3. They both have a 1/3 F. They both have a 6 minus F. And this term has a 6 minus F. And that term does not have anything left. Something about this feels very wrong. It does have something left. 1/3 F. Oh, it has another F. There we go. You can clean that up a little bit if you like. You could probably leave it this way, for real. I'm going to clean up a little bit because I'm just feeling that this is sort of gross. 1/9 F, and then 6 minus F, and 6 minus 2F. That's it. Okay, it's a little bit gross, but it worked. So we also have another thing to do. And it is right here, part D. Use Euler's method. All right, fun. Starting at t equals 0, with 2 steps of equal size to show the total amount of liquid fertilizer injected into the growing system by t equals 1 month. Show the computations that lead to your answer. Let's just go ahead and deal with part 1, and then we'll deal with part 2 later. And then it's asking for an overestimate or underestimate, and then we'll talk about that in terms of concavity. It'll be great. Part D is asking us to use Euler's method. Now, in the past, when I have used Euler's method, and I'm going to grab some old scrap paper that I've been using, I would have x, I'd have y, and then I would have some variation of y equals mx plus b. Okay, that is Euler's method at its most basic. But instead of m, we're going to have dy dx. Instead of x, we're just increasing by some amount every time. And instead of b, it's another y value. So that's what I really have. Now, I'm not going to write that because what I'm really going to write is not x's and y's, but it's going to be time and fertilizer. So here's my chart, but with time and fertilizer. So time, fertilizer, and then my df dt, which they told me already what it was, times the delta x. Let's rephrase that. Delta time. How much we're increasing each time. And I need to read the problem again before we do that. And it is going to look like this. Start at 0. End at 1. 2 steps of equal size. So we're increasing by 1/2 each time. So 1/2 each time. And then plus f. So here's your m x plus b. Just say it. Okay. All this by hand, no calculator. 0, 1/2, 1. When you get right here, you finished. All right, at 0, we had 3. How do you know? They told you. They told you. They told you. It was right there. T equals 0, 3 liters of liquid fertilizer, and yeah, it was fun. So let's start plugging in some things and cranking out some answers. So 1/3 times 3 times 6 minus 3. We've actually already done this process. Times 1/2, and then plus 3 again. And I am going to go a little bit faster here, and I'm double checking to make sure that what I have is what I had when I worked this out. Yeah, 9/2. I'd love to waste your time going through that whole process. That's 9/2. So we have 9/2 there, and we'll plug it in here as well. So 1/3 times f, and then 6 minus f times 1/2, and then plus f again. And that gives me lots of fantastic math, and it gives me 45/8, actually, which goes here, and that is my answer for the Euler's method. Now, there's another part to it, but we will take care of that in just a moment. All right, so here goes. Let's read the problem again, make sure we understand what it's asking. Use Euler's method and to approximate the total amount of liquid fertilizer injected. Done. Show the computations that lead to your answer. I'm reluctant to leave it like this. I really want to say that I want to give an answer. I want to say, okay, well, the approximation is 45/8. So let's do that. The approximation using Euler's method for t equals 1 is 45/8 liters. All right, fantastic. Now we're still not done. We have to continue reading and move on to the next part. And the next part says, is the approximation an overestimate or an underestimate for the total amount of liquid fertilizer injected into the growing system by time t equals 1 month? Give a reason for your answer. Okay, is it an overestimate? Is it an underestimate? I don't know, but here's what I do know. And this is going to be kind of intuitive once we realize that we're really looking at a graph. I need the second derivative, but I don't need the second derivative. Beyond this value, from 3 to 6, the graph is concave down, right? It is, because we're increasing towards 6 and becoming concave down. So, here goes. Our approximation is going to be an overestimate. I'm going to start writing that. The approximation because f of t is concave down for all, not t values, but for all the f values. You could call them y values if you wanted to, between 6 and 3.